Hello everybody, good morning. Myself, Dr. Shubhankar Sen, an Associate Professor from the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the second lecture of Module 7 of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall illustrate the computation of consistent mass matrices for the two-noded and three-noded bar elements along with the linear triangular elements. So we shall show the computations by using exact integration, and few cases we shall also show by using the Gauss quadrature. The mass matrix that is directly obtained from the parabolic PDEs are known as consistent mass matrices, denoted by the symbol MIJE at the element level. It is found that these mass matrices are symmetric, diagonally dominant, positive definite, as well as linearly independent. So this linear independence is a major distinguishing feature of this MIJE relative to the stiffness counterparts KIJE. We have shown that the stiffness matrices KIJE obtained from the elliptic partial differential equations, they are always linearly dependent. So this marks a fundamental difference where in consistent mass matrices we do not have any expression for derivatives of shape functions. Rather, we have the expressions for product of shape functions themselves. The consistent mass matrices are defined as MIJE equals to integration over omega e psi IE psi JE d omega e. So if our governing equation or the unsteady heat diffusion equation, suppose in one dimension, if we write it as rho Cp del T equals to K del 2T del X2. Suppose let us ignore the source term. This is only for illustration purpose. So in this case, we can represent the mass matrix. Then the mass matrix may be represented as MIJE equals to rho into integration over omega e psi IE psi JE d omega e, where rho is the material density and Cp is the specific heat and capital K is the thermal conductivity. If the governing equation is represented as del T equals to alpha del 2T del X2, then mass matrix may be expressed as MIJE equals to integration over omega e psi IE psi JE d omega e. So we shall follow the second presentation of the governing equation. So we shall calculate our mass matrices based on this expression. So let us begin with the two-noded bar elements. Calculation of MIJE for bar elements. So we consider case 1 for two-noded or linear bar elements. So we have a two-noded bar element. This is element E with local nodes 1 and 2. Its mesh size is delta x. This is in the global coordinate system x. The same element we can represent in the natural coordinate system with the natural coordinate xi. So the local nodes 1 and 2 in the master plane, and the coordinates of the left and right nodes are xi equals to -1 and xi equals to 1 respectively. So at the midpoint we have the origin of the coordinate system xi equals to 0. So we begin our calculations as MIJE equals to integration over omega e psi ie psi je d omega e, where because of two nodes I will vary from 1 to 2 and j will also vary from 1 to 2. This can be represented as integration over omega e cap psi ie xi psi j xi d omega e. This is dx. So d omega e equals to dx equals to determinant of je into d xi. So we can write it as determinant of je into d xi. Determinant of je is constant equals to half of the mesh size. So this we can write as delta x by 2 integration from -1 to 1 psi ie xi psi je xi d xi. When I equals to 1 and j equals to 1, for I equals to 1 and j equals to 1, we have M11E equals to delta x by 2 integration -1 to 1 psi 1 is xi into psi 1 is xi. We have psi 1 is xi whole square d xi. Now psi 1 is xi, this is half of 1 minus xi, and psi 2 is xi equals to half of 1 plus xi. So this expression, it reduces to delta x by 2 integration -1 to 1 1/4 into 1 minus xi whole square d xi. This is equals to delta x by 8 integration -1 to 1 1 minus 2 xi plus xi square d xi. This gives us M11E equals to delta x by 8 into, after integration we have xi minus 2 into xi square by 2 plus xi cube by 3. This is from -1 to 1. This reduces to delta x by 8. Then we have 1 minus 1 plus 1/3 minus, here we have -1 minus 1 minus 1/3. This simplifies as delta x by 8 into, here we have 1/3 plus 2 plus 1/3. So this reduces to M11E equals to delta x by 8 into 2 plus 2/3. 2 plus 2/3 equals to delta x by 8 into 8 by 3. This is equals to delta x by 3. Now we can similarly calculate the remaining 3 terms. So for I equals to 1 and j equals to 2, we have M12E equals to delta x by 2 integration -1 to 1 psi 1e is half into 1 minus xi, and psi 2 is half into 1 plus xi into d xi equals to delta x by 8 integration minus 1 to 1 minus xi square d xi. This reduces to delta x by 8 into xi minus xi cube by 3. Range is from minus 1 to 1. This is delta x by 8, 1 minus 1/3 minus minus 1 plus 1/3. This is equals to delta x by 8 into 1 minus 1/3 plus 1 minus 1/3 equals to delta x by 8 into 2 minus 2/3. So this is giving us delta x by 8 into 4 by 3 equals to delta x by 6. Now for I equals to 2 and j equals to 1, we get m21e equals to delta x by 2 integration minus 1 to 1 half of 1 plus xi into half of 1 minus xi d xi. This is exactly the same expression which we got for m12e. So this is equals to m12e equals to delta x by 6 from symmetry. Now we are left with the second diagonal term. For I equals to 2 and j equals to 2, we have m22e equals to delta x by 2 integration minus 1 to 1 psi 2e whole square d xi equals to delta x by 2 integration minus 1 to 1 half of 1 plus xi whole square d xi. So this is delta x by 8 integration minus 1 to 1 plus 2 xi plus xi square d xi. This gives us delta x by 8 into xi plus 2 into xi square by 2 plus xi cube by 3. The range is from minus 1 to 1. This can be simplified as delta x by 8 into 1 plus 1 plus 1/3 minus minus 1 plus 1 minus 1/3. This reduces to delta x by 8 into 2 plus 1/3 plus 1/3 equals to delta x by 8 into 2 plus 2/3 equals to delta x by 8 into 8 by 3 equals to delta x by 3. We have therefore calculated all the components of the consistent mass matrix for the two-noded bar element. We can summarize this matrix as the consistent mass matrix for the two-noded bar elements may therefore be expressed as m e equals to m ije equals to m11e, m12e, m21e, m22e. So m11e, it was delta x by 3, m12e, it was delta x by 6, m21e, this was also delta x by 6, and m22e was delta x by 3. So this can be represented as delta x by 6 to 2, 1, 1, 2. So we can see that the matrix is symmetric, diagonal dominant, and linearly independent. By taking a product of this matrix with respect to a non-null vector, it can be proved easily that this is also a positive definite matrix. It can be shown also to be positive definite. So, by exact integration in the natural coordinate system, we have calculated the consistent mass matrix for the two-noded bar elements. We can show one case of this calculation by using Gauss quadrature. Let us illustrate Gauss quadrature computations for M11E. We know that M11E equals to delta x by 2 integration minus 1 to 1 psi 1 is I whole square d xi. This can be written as delta x by 2 integration minus 1 to 1 half of 1 minus xi whole square d xi. This is delta x by 8 integration minus 1 to 1 1 minus xi whole square d xi. So this is the integrand f of xi. This can be written as delta x by 8 summation of f of xi I wi, where I is varying from 1 to ngp. Now f xi is a quadratic function in xi, indicating that the order of the polynomial is p equals to 2. Therefore, the number of Gauss points, the number of Gauss or integration points equals to ngp equals to p plus 1 by 2. So this is 2 plus 1 by 2. This is 1.5. So we can take the nearest integer which is higher than 1.5. This is taken as 2. Therefore, we shall employ 2-point quadrature for MIJE terms. Now, here, this is our master element. So this is xi. This is xi equals to 1, local node 2. This is local node 1, xi equals to minus 1. This is the origin of the coordinate system. This is xi equals to 0. Now, our Gauss points are xi 1 equals to minus 1 by root 3 and xi 2 equals to 1 by root 3. Our w1 equals to 1 and w2 equals to also 1. So our integrand, it was delta x by 8 into summation of f xi I wi. I is varying from 1 to ngp. Therefore, M11E equals to delta x by 8 summation I equals to 1 to ngp. Ngp is 2 f of xi I wi equals to delta x by 8 into f of xi 1 w1 plus f of xi 2 w2. So here we get delta x by 8 into function of xi 1 is minus 1 by root 3, w1 is 1, f of xi 2, our xi 2 is 1 by root 3, our w2 is 2. So this gives us delta x by 8 into f of minus 1 by root 3 plus f of 1 by root 3. Now f of xi, this is 1 minus xi whole square. So here we can see that this reduces to delta x by 8 1 minus xi whole square, where xi equals to minus 1 by root 3 plus 1 minus xi whole square, where xi equals to 1 by root 3. This reduces to delta x by 8 into 1 plus 1 by root 3 whole square plus 1 minus 1 by root 3 whole square. So this is delta x by 8 into 1 plus 2 by root 3 plus 1 by 3 plus 1 minus 2 by root 3 plus 1 by 3. So this becomes delta x by 8 into 2 plus 2 by 3 equals to delta x by 8 into 8 by 3 equals to delta x by 3. This value we have already obtained by exact integration in the natural coordinate system. Now we go for the case 2. We shall calculate the entries of the consistent mass matrix of a 3-noded bar element or a quadratic bar element. So this is for case 2. Quadratic bar element. So this is the quadratic bar element with local nodes 1, 2 and 3. This is in the global coordinate system x. So this is our mesh size delta x, and in the natural coordinate system we have the local nodes 1 with xi equals to minus 1, local node 2 with xi equals to 0 and local node 3 with xi equals to 1. Here our Mij equals to integration over omega e psi I e psi j e d omega e equals to integration over omega e cap psi I e xi psi j e xi determinant of the Jacobian matrix into d xi. Now we already know that determinant of the Jacobian matrix for a bar element, it is half the mesh size irrespective of the order of the shape functions or irrespective of the order of the element. So we can simply write it as determinant of j equals to half the mesh size equals to delta x by 2 integration minus 1 to 1 psi I e xi psi j e xi d xi. So now we make the calculations where I equals to 1 to 3 and j is also varying from 1 to 3. Here this Gauss weight at integration point 2, this is certainly 1. So let us calculate m ije equals to delta x by 2 integration minus 1 to 1 psi I e xi psi j e xi d xi in the natural coordinates. This is xi direction, this is local node 1, local node 2, local node 3. So xi equals to minus 1, xi equals to 0 and xi equals to 1. We know that psi 1 is xi equals to minus xi by 2 plus xi square by 2. Psi 2 is xi equals to 1 minus xi square and psi 3 is xi equals to xi by 2 plus xi square by 2. For I equals to 1 and j equals to 1, we get m11 e equals to delta x by 2 integration minus 1 to 1 psi 1 is xi into psi 1 is xi. So this is psi 1 is xi whole square d xi. So this is equals to delta x by 2 integration minus 1 to 1 psi 1 is xi is minus xi by 2 plus xi square by 2 whole square d xi, this is equals to delta x by 2 integration minus 1 to 1, this is xi square by 4 minus xi cube by 2 plus xi to the power 4 by 4 d xi. Performing the integration, we get here delta x by 2 into xi cube by 12 minus xi to the power 4 by 8 plus xi to the power 5 by 20. The range is from minus 1 to 1. This is equals to delta x by 8 into xi cube by 3 minus xi to the power 4 by 2 plus xi to the power 5 by 5 from minus 1 to 1. This gives us delta x by 8 1/3 minus half plus 1/5 minus 1/3 minus half minus 1/5. This becomes delta x by 8 1/3 minus half plus 1/5 plus 1/3 plus half plus 1/5. From here, half and half they cancel out, so we get delta x by 4. We have 1 by 3 two times and 1 by 5 two times, so we can make it delta x by 4 into 1/3 plus 1/5. So this gives us delta x by 4 into 8 by 15 equals to 2 delta x by 15. So we have calculated the first term of this matrix. This comes as 2 delta x by 15. Now for I equals to 1 and j equals to 2, we can calculate m1 to e equals to delta x by 2 integration minus 1 to 1 psi 1 is I into psi 2 is I d xi. This gives us delta x by 2 integration minus 1 to 1 psi 1 is I is minus xi by 2 plus xi square by 2 psi 2 is I is 1 minus xi square d xi. So this can be written as m1 to e equals to delta x by 4 integration minus 1 to 1 minus xi plus xi square into 1 minus xi square d xi equals to delta x by 4 integration minus 1 to 1. We have minus xi plus xi square plus xi cube minus xi to the power 4 d xi equals to delta x by 4. After integration we get minus xi square by 2 plus xi cube by 3 plus xi to the power 4 by 4 minus xi to the power 5 by 5. It is varying from minus 1 to 1. Here we get delta x by 4 into minus half plus 1/3 plus 1/4 minus 1/5 minus, here we get minus half minus 1/3 plus 1/4 plus 1/5. This we can write as delta x by 4 minus half plus 1/3 plus 1/4 minus 1/5 plus half plus 1/3 minus 1/4 minus 1/5. So here we see that this plus 1/4 and minus 1/4 minus half and plus half, they cancel out. We are left with 1/3 2 times and minus 1/5 2 times. So this can be written as M12 E equals to delta x by 4 into, here you can see this is 1/3 2 times. So this is 2 into 1/3 minus 1/5. So this is 2 into 1/3 minus 1/5. This can be simplified as delta x by 2 into 2 by 15 equals to delta x by 15. Now for I equals to 1 and j equals to 3, we have M13E equals to delta x by 2 integration minus 1 to 1 psi 1e xi psi 3 xi d xi. This gives us M13E equals to delta x by 2 integration minus 1 to 1 minus xi by 2 plus xi square by 2, and here we have xi by 2 plus xi square by 2 d xi. This gives us delta x by 2 integration minus 1 to 1. So this is xi to the power 4 by 4 minus xi square by 4 d xi. This is delta x by 8 integration minus 1 to 1 xi to the power 4 minus xi square d xi. This is delta x by 8 into xi to the power 5 by 5 minus xi cube by 3. So this is delta x by 8 into 1/5 minus 1/3 minus 1/5 plus 1/3 equals to delta x by 8 into 1/5 minus 1/3 plus 1/5 minus 1/3 equals to delta x by 8 into 2 into 1/5 minus 1/3 equals to delta x by 4 into 3 minus 5 by 15 equals to minus delta x by 4 into 2 by 15 equals to minus delta x by 30. So we have calculated the first row of the mass matrix of the 3-noded bar element. Similarly, it can be shown for the remaining rows. Now we can construct the mass matrix. Similarly, we can calculate M21E, M22E, M23E, M31E, M32E, and M33E. By symmetry, we already know that M21E equals to M12E and M31E equals to M13E. We summarize our result here for the 3-noded bar element. ME equals to M11E, M12E, M13E, M21E, M22E, M23E, M31E, M32E, M33E. Our M11E, this was 2 delta x by 15. So this is 2 delta x by 15. Our M12E, this was delta x by 15, and our last term was minus delta x by 30. By symmetry, we can simply write the M21E term as delta x by 15, and similarly the 31 term we can write as minus delta x by 30. So it can be shown here that M32E, this will also be delta x by 15, and accordingly M23 will be delta x by 15. The last diagonal term M33E, this will be 2 delta x by 15, and the M22E term, it will be 8 delta x by 15, so that we can represent it as delta x by 30 into 4 to minus 1 to 16 to minus 1 to 4. So we have calculated the entries of the quadratic bar element by using exact integration. Now we show this calculation for M11E term using the Gauss quadrature. Calculation of M11E using Gauss quadrature. Mij equals to integration over omega e psi I psi j d omega e equals to delta x by 2 integration from minus 1 to 1 psi I e xi psi j e xi d xi. For I equals to 1 and j equals to 1, M11E equals to delta x by 2 integration minus 1 to 1 psi 1 is I whole square d xi. This gives us delta x by 2 integration minus 1 to 1 minus xi by 2 plus xi square by 2 whole square d xi. So if we look into this expression, this gives us a fourth order polynomial. This gives us a fourth order integrand. It means that p equals to 4. Therefore, number of Gauss points equals to p plus 1 by 2 equals to 4 plus 1 by 2 equals to 2.5. Roughly, we take 3-point quadrature. Therefore, we shall perform 3-point quadrature for the quadratic bar elements. Now, if we take our master element here, this is the natural coordinate, local coordinate xi equals to minus 1 for local node 1, for the local node 2, xi equals to 0, and for the local node 3, xi equals to 1. We have 3 quadrature point. This quadrature point xi 1 equals to minus square root of 3 by 5. The second quadrature point is at the origin, and the third quadrature point, that is xi 3 equals to square root of 3 by 5. Our weights are W1 equals to 5 by 9, W2 equals to 8 by 9. We have already discussed all these features, and W3 is also equal to W1 equals to 5 by 9. So here we have M11E equals to delta x by 2 integration minus 1 to 1 f xi d xi. Here f xi equals to xi square by 2 minus xi by 2 whole square. So here we can simplify it as m11e equals to delta x by 8. We can take the 2 outside, integral minus 1 to 1 xi square minus xi whole square d xi. So we have our f xi as xi square minus xi equals to delta x by 8 summation I equals to 1 to ngp f of xi I wi equals to delta x by 8 into f of xi1 w1 plus f of xi2 w2 plus f of xi3 w3. Now f of xi1 w1, this is xi square minus xi whole square, where xi equals to minus square root of 3 by 5 into w1, this is 5 by 9. So we have xi square is 3 by 5 and minus xi, this will be plus square root of 3 by 5 whole square into 5 by 9. So this will be 3 by 5 minus 6 by 5 into square root of 3 by 5 plus 3 by 5 into 5 by 9. This is the first contribution. F of xi2 w2 equals to xi square minus xi whole square, where xi equals to 0 into 8 by 9. So this will be 0 into 8 by 9 equals to 0. F of xi3 into w3 equals to xi square minus xi whole square, at xi equals to square root of 3 by 5 into 5 by 9. This is equals to square root of 3 by 5 whole square. So this is 3 by 5 minus square root of 3 by 5 whole square into 5 by 9. This is there was a small error. This is certainly 3 by 5 whole square in the first place. So here we have 9 by 25 minus 6 by 5 into square root of 3 by 5 plus 3 by 5 into 5 by 9. So here we can combine all three of them and then we get the integrand. Here this is positive. So m11e equals to delta x by 8 into f of minus square root of 3 by 5 into 5 by 9 plus f of 0 into 8 by 9 plus f of square root of 3 by 5 into 5 by 9. This gives us delta x by 8 into f of minus square root of 3 by 5. This will be 9 by 25. 9 by 25 minus 6 by 5 into square root of 3 by 5. 6 by 5 into square root of 3 by 5 plus 3 by 5 multiplied with 5 by 9 plus 0 plus 9 by 25 plus 6 by 5 into square root of 3 by 5 plus 3 by 5 multiplied with 5 by 9. This gives us delta x by 8 into 9 by 25 plus 3 by 5 into 5 by 9 into 2, because this 6 by 5 into square root of 3 by 5, it cancels from both sides. Then we have the same quantity, 9 by 25 plus 3 by 5 whole multiplied by 5 by 9 2 times. This gives us delta x by 4 into 25 at the bottom, 9 plus this is 15 into 5 by 9. So this is delta x by 4 into 24 by 25 into 5 by 9. So this is reducing to 5, 6, 2, 3. This is 2 delta x by 15. We found exactly the same value while doing the exact integration from the M11 term. So this ends for the illustration of the calculation of mass matrix in the consistent state for the 3-noded bar element. Let us calculate for one term. We shall show the mass matrix component for the linear triangular element. So case 3, calculation of consistent mass matrix for 3-noded or linear triangular elements. So let us consider an arbitrary triangular element. So this is element E, local nodes 1, 2, 3. This is the global coordinate system xy. The coordinates are global coordinates x1e, y1e for node 1. This is x2e and y2e for node 2. And finally for node 3, we have x3e, y3e. Our expression for Mij is Mij equals to integration over omega e psi I psi j d omega e. We shall perform this computation in the natural coordinate system. Perform this computation in natural coordinates. Let AE equals to area of element E that we have shown here. Our master element we are showing here. This is the xi axis, this is the eta axis, local node 1, local node 2, local node 3. At local node 1, the origin is placed. We have here 1, 0, and here we have 0, 1. So psi 1e xi eta equals to 1 minus xi minus eta. Psi 2e xi eta equals to xi, and psi 3e xi eta equals to eta. These are the shape functions in the natural coordinate system. This is our master element E cap. So master element for the linear triangular element. Here this should be positive and this should be negative. Our integrand was Mij equals to integration over omega e psi I psi j d omega e. This can be represented as integration over omega e cap psi I a function of xi eta, psi j a different function of xi eta, d omega e cap. This we can simplify as integration over omega e cap psi I xi eta psi j xi eta into determinant of je into d xi d eta. For triangular elements, determinant of je equals to twice the area of the element equals to a constant. So this gives us Mij equals to determinant of Je integration over omega e cap psi ie xi eta psi Je xi eta d xi d eta equals to 2 into area integration from 0 to 1. This is the range of xi. The range of eta is eta equals to 0 to 1 minus xi psi ie xi eta psi Je xi eta d eta d xi. Let us consider I equals to 1 and j equals to 1. This gives us M11E equals to twice area integration from 0 to 1 integration from 0 to 1 minus xi psi 1e xi eta whole square d xi d eta equals to twice ae integration 0 to 1 integration 0 to 1 minus xi 1 minus xi minus eta whole square d eta d xi. Let us consider 1 minus xi minus eta equals to z. This gives us d eta equals to minus dz. When eta equals to 0, then z equals to 1 minus xi. When eta equals to 1 minus xi, then z equals to 0. So this gives us M11E equals to 2ae integration from 0 to 1 integration from, when you transform d eta to dz, our limit changes from 1 minus xi to 0. So 1 minus xi to 0. 1 minus xi minus eta was z. So this is z square. Now d eta has become dz. So it is minus dz d xi. This gives us minus 2ae integration from 0 to 1 integration from 1 minus xi to 0 z square dz d xi. This is minus 2ae integration 0 to 1. Here z square dz, it gives us z cube by 3. The range is 1 minus xi to 0 d xi. This is equals to minus 2ae by 3 integration 0 to 1. Our z cube, here we get 0 minus 1 minus xi whole cube d xi. So this can be represented as 2ae by 3 integration 0 to 1 1 minus xi whole cube d xi. We can simplify this further by taking 1 minus xi another variable. Let 1 minus xi equals to t. This gives us d xi equals to minus dt. When xi equals to 0, t equals to 1, and when xi equals to 1, t equals to 0, this gives us 2ae by 3 integration, when xi is 0, t is 1, when xi is 1, t is 0, 1 minus xi whole cube is t cube, and d xi is minus dt, so this is minus dt, so minus 2ae by 3 integration 1 to 0 t cube dt equals to minus 2ae by 3 into t to the power 4 by 4, where t is varying from 1 to 0. This is minus 2AE by 3 into 4. Here we have 0 minus 1. So this is 2AE divided by 12, or this is equals to AE divided by 6. Similarly, it can be shown that M12E equals to AE by 12 and M13E is also equal to AE by 12. Therefore, from symmetry, the consistent mass matrix may be expressed as ME equals to M11E, M12E, M13E, M21E, M22E, M23E, M31E, M32E, M33E. So our M11E, it was AE by 6. So this is AE by 6. The remaining two terms in the first row, they are AE by 12, AE by 12. In the second row, we have AE by 12, AE by 6, AE by 12. In the third row, we have AE by 12, AE by 12, AE by 6. So we can take AE by 12 outside and then we can get it as 2, 1, 1, 1, 2, 1, 1, 1, 2. So this is the final expression for consistent mass matrix of a three-noded or linear triangular element. We conclude today's class here. In today's class, we have shown the calculation of consistent mass matrices for two-noded and three-noded linear bar elements. We have also considered triangular element of linear type. In each case, the consistent mass matrix is symmetric, diagonally dominant, positive definite, and certainly linearly independent. For today's class, I suggest that students should follow the textbooks by Professor T.J.R. Hughes as well as Professor J.N. Reddy. Thank you very much for attending my lecture.